So, scalability is the term used to describe the system's ability to cope with increased load. Now, first, we need to describe the current load on the system. Only then can we discuss growth questions. So, load can be described with a few numbers, which we call load parameters. And the best choice of parameters depends on the architecture of your system. Requests per second to a web server, the ratio of reads to writes in a database, the number of simultaneously active users in a chat room, the hit rate on a cache, etc. And perhaps the average case is what matters for you. Or perhaps your bottleneck is dominated by a small number of extreme cases. So, to make this idea more concrete, let's consider Twitter as an example, using the data published in November 2012. So, two of the main components or operations of Twitter are post tweet and home timeline. So, in the post tweet operation, a user can publish a new message to their followers, and as per their data, they get 12,000 requests per second at max. And home timeline means that a user can view tweets posted by the people they follow. And home timeline gets 300,000 requests per second. Now, simply handling 12,000 writes per second would be fairly easy. But Twitter's scaling challenge is not primarily due to tweet volume, but due to fan out. So each user follows many people and each user is followed by many people. So now let's look at two ways of implementing post-tweet and home timelines operations, and then let's compare their performances as well. So in the first implementation of post-tweet, whenever a user tweets something, we insert the new tweet into the global collection of tweets. And for the home timeline, we look up all the people they follow, find all the tweets for each of those users, and merge them sorted by time. Now, let's see how this implementation could be written as a query. So, this query selects all the columns from the tweets and the users table, and then performs a join on the tweets and the users table. This join basically retrieves the user information associated with each tweet. After that, there is another inner join which is between the result of this join and the follows table. This ensures that only users who are followed by someone are included in the results. And then at the end there is a where clause which restricts the results to only those rows where the follower ID in the follows table matches the current user. So in summary, the query retrieves all tweets and the associated user information for those tweets, but only for tweets sent by users that the current user is following. Now let's look at the second approach. So here, we maintain a cache for each user's home timeline. So whenever a user posts a tweet, we look up all the people who follow that user and insert a new tweet into each of their home timeline caches. So for the home timeline operation, we directly fetch the tweets from the cache. Now this diagram basically represents Twitter's data pipeline for delivering tweets to followers. So let's say that a user posts a tweet and there is a global collection of tweets. So that tweet will go into this global collection or the database, and then for maintaining the home timeline caches or for populating them, the fan out operation is done, which basically delivers tweets to each followers. So let's say that this is user 1 and he follows some people. And if those people post a tweet, they will go into the user 1's home timeline cache. Similarly for user 2 and user 3 as well. So for the home timeline operation for user 1, the tweets will be directly fetched from the home timeline cache of user 1. Now, the second approach works because the average rate of published tweets is almost 2 orders of magnitude lower than the rate of home timeline reads. And so in this case, it's preferable to do more work at write time than read time. But there is a downside to approach 2 as well. So on average, a tweet is delivered to about 75 followers. So 4.6 thousand tweets per second become 345,000 writes to home timeline caches. But what about someone with over 30 million followers? Do we do 30 million writes to home timelines? Now, doing this in a timely manner where Twitter tries to deliver tweets to followers within 5 seconds is a significant challenge. So, Twitter is moving to a hybrid approach of both the first and second approach. Now, most users' tweets continue to be fanned out to home timelines at the time when they are posted. But a small number of users with a very large number of followers, that is celebrities, are accepted from this fan out. Tweets from any celebrities that a user may follow are fetched separately and merged with the user's home timeline when it is read, like in approach 1. Once you have described the load, you can investigate what happens when the load increases. So you can look at it in 2 ways. So when you increase the load parameter and keep the system resources the same, how is the performance of the system affected? And second is when you increase the load parameter, how much do you need to increase the resources if you want to keep the performance the same? So in batch processing system like Hadoop, we care about throughput, which is the number of records we can process per second. Whereas in online systems, we care about the service's response time, which is the time taken between a client sending a request and receiving a response. And even if you only make the same request over and over again, you'll get a slightly different response time on every try. This graph here shows a distribution of response times for a sample of 100 requests to a service. Now, it is common to see the average response time of a service reported. However, the mean is not a very good metric if you want to know your typical response time, because it doesn't tell you how many users actually experience that dealing. So usually it is better to use percentiles. So if you take your list of response times and sort it from fastest to slowest, then the median is the halfway point. Now for example, if your median response time is 200 milliseconds, then that means that half your requests return in less than 200 milliseconds and half your requests take longer than that. So the median is also known as the 50th percentile, which is abbreviated as P50. And in order to figure out how bad your outliers are, you look at higher percentiles, the 95th, the 99th, and the 99.9th percentile, which are abbreviated as P95, P99, and P999. So these are the response time thresholds at which 95%, 99%, or 99.9% of requests are faster than that particular threshold. So this we have covered, the average, percentiles, and median. This is the theory. So high percentiles are also known as tail latencies. And percentiles are often used in service level objectives and service level agreements. These contracts define the expected performance and availability of a service and set expectations for client of the service and allow customers to demand a refund if the SLA is not met. Now, queuing delays often account for a large part of response time at high percentiles. Now, as a server can only process a small number of things in parallel, it only takes a small number of slow requests to hold up the processing of subsequent requests. And this phenomenon is commonly known as head of line blocking. Now, when several backend calls are needed to serve a request, it just takes a single slow backend request to slow down the entire user request. Now, in this example, let's say that there is one request which needs all of these backend calls to be made to complete the request. So, there is one backend call which takes 487 milliseconds to complete. So it doesn't matter that backend 1 took 92 milliseconds or backend 5 took 86 milliseconds. The entire request will take 487 milliseconds or more than that. And this is called tail latency amplification. It is when a request is being slow because the end user requires multiple backend calls and some of them are slow. Now let's talk about some terminologies here. So, latency versus response time. So, response time is what the client sees. Besides the actual time to process the request, it includes network delays and queuing delays. Whereas latency is the duration that a request is waiting to be handled, during which it is latent or awaiting service. So, approaches for coping with load. Now, there are two main approaches, scaling up and scaling out. So, scaling up is also known as vertically scaling, which means moving to a more powerful machine. And scaling out is also called horizontal scaling, which means distributing the load across multiple smaller machines. This is also known as shared nothing architecture. Now, there are some systems which are elastic, which means that they can automatically add computing resources when they detect a load increase. Such systems are used for highly unpredictable loads. So while distributing stateless services across multiple machines is fairly straightforward, taking stateful data from a single node to a distributed setup introduces a lot of complexity. The architecture of systems that operate at a large scale is usually highly specific to the application. For example, a system that is designed to handle 100,000 requests per second, each 1 kilobyte in size, looks very different from a system that is designed for 3 requests per minute, each 2 gigabytes in size, even though the two systems have the same data throughput.